So we want to start by finding the derivative of each of our terms. We have 4 terms. Each term has its own derivative. So we want to start by taking the derivative of this x squared. So I might even do this. I might make this x to the 1/2 plus y to the 1/2 equals 3 plus y. Because now what we're going to do is take the derivative of our x to the 1/2 using the power rule. So this is going to be 1/2 square root of x in simplified radical form. And then this one is going to be a little bit different just because we have that chain rule component to remember whenever we have something in terms of y when we're trying to take the derivative with respect to x. So it's going to be the exact same thing, but because of the chain rule, we're going to have the derivative of the inside as well. Our inner function in this case would be just y. The outer one would be the 1/2 power. So it's going to be the same thing as we had before with the y prime. And then on the other side, derivative of 3 is 0. And then the derivative of y is just y prime. Notice how we don't have anything attached to the y. We don't have an exponent, we don't have a radical, we don't have anything attached to it at all. So it's simply just going to be y. All right, so we have 2 terms involving the derivative of y. Or I meant to say y prime right there. Sorry about that. We simply have y prime. So I can see that 2 out of our 3 terms have the derivative of y. So I want to move this term over to the right by subtraction. All right, and then we just want to factor out a y prime from both of our terms right here. And I'm going to move this up, give myself a little more room to work. So factoring out a y prime, we're going to get this. We're going to get 1 minus 1/2 square root of y. And then we have that equals, same thing, 1/2 square root of x. So we want to divide everything by this binomial inside the parentheses. So we're going to divide both sides by this, and we're going to get y prime equals 1/2 root x times 1 minus 1/2 square root of y. So we could simplify this. We could make this one distribute with the 1 and then also distribute with the second term so that the second term would get us negative 1/4 square root of xy under the same radical. But like I said, that's not really the focus of this class. The focus of this class is just mainly learning calculus. But in the future, if I do assign homework with problems like this, I would like you to simplify it. Just makes it easier to grade when all of the answers are in the exact same form. So please simplify if you're turning in something for homework or if you have it on the quiz. So, like I said, we're going to spend the next 10 minutes or so, the last 10 minutes of class, talking about why this is important. You might be thinking that derivatives we've been learning up until now, the normal derivatives explicitly work. They work just fine. They give us a great deal of information. So why do we have to learn all of this stuff anyway? How is this useful? The next chapter will make it all clear. It'll make it clear why this is such a useful tool to have in our calculus arsenal. So the next topic we're going to talk about is related rates. And we're going to just give a general introduction, but I think next time we're going to get more in depth on this subject, on what related rates really are. So let's talk about this real quick. So we know what rates are. Calculus is the science of rates. Calculus tells us how fast things are changing in regard to other things, how fast y is changing in respect to x, where y could be any quantity. It could be any real life quantity that we're measuring, and same with x. So when you drive a car, and you're trying to figure out how fast you're going, your speedometer gives you a number in miles per hour. That's a rate. So the derivative of position, and like I said, we're not really going to be going into things like this that much. This is more of a physics concept, but I feel like it would be really good to help us learn this a little more clearly. So the derivative of position, and the position is typically denoted like this. They typically call it x of t in a physics class. So x is a position that depends on time. That would get us that would get us velocity. The derivative of position is velocity. So this would be v of t. So every time you look at the speedometer on your car and your car tells you how fast you're going, your car is actually solving a calculus problem when it gives you the current rate at which you're traveling. So rates are very, very important in calculus. It's one of the main underlying themes that we'll be exploring throughout this class. Figuring out rates and using them to solve a wide range of different problems. So related rates deal with things that are increasing in relation to other things that might be increasing or decreasing. So let me find what I think might be a good example to illustrate this a little bit better. Give me a second. I found a good one in my book. So we have this to work on. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. Volume is increasing, so we already have a rate of change for our volume. Our volume is increasing with respect to time. And then we want to find how fast the radius of the balloon is increasing when the diameter is 50 centimeters. Let me just add that real quick. Diameter is 50 centimeters. So this is one of the more general topics in calculus where we realize a visual approach is really helpful. This is one of the topics where it's easy to get a really good idea of the problem just by drawing a picture. So this is our balloon. And I warn you in advance, I'm a really terrible artist, so don't expect anything really good from this. So we have a balloon, and of course we want to make sure that it's clear that this is a three-dimensional figure. This is a sphere. I don't know, something like that. It'll work. And of course, every sphere has a center, and then it also has a radius. So just like with a circle, it doesn't matter which point on the exterior of the balloon we're pointing to from the center. Those points will all be equidistant from our center. So let's take a look at what they're asking for and what information they give us. They want us to find how fast the radius of the balloon is increasing when the diameter is 50. And then the other information we're given is the fact that the volume is increasing at a rate of 100 centimeters cubed every second. That is our derivative of the volume with respect to time. So let's try and see if we can think of an equation that will kind of connect all of those together, and then we'll be able to use implicit differentiation to find the answer that they're asking us for. So I think I want to start by seeing if there is an equation we can use. There's probably a pretty common one we can use that connects all of our pieces of information together. So we have a radius, we have diameter, we have volume. So we have a really handy formula for that ready to go. We have the volume of a sphere, S-P-A-G-R, volume of the sphere, of course, is 4/3 pi r cubed. And interestingly enough, you'll learn where this comes from, I think, over the maybe next month, I think, is when we're going to be getting into where this stuff comes from. But for now, this is all we need. So we don't have the volume. Let's see what information we do have, though. We know what the rate of change for the volume. And you know what? I think I'm just going to call it V from now on. We already know it's a sphere, so I'm going to just write V is 4/3 pi r cubed. So now what we want to do is apply our implicit differentiation to find what they're asking us to find. So we have derivative of this, derivative of volume. We're going to just call this derivative of volume with respect to some other variable. In this case, we're dealing with time, so it will be the derivative of the volume with respect to time. And then we have just one single term on the other side. I want to treat this as if it were a constant. Well, it actually is a constant, 4 pi over 3. So now when we apply the product rule for this to find the derivative of this entire thing, we're going to have the derivative of the first. So the derivative of a constant is always 0 times a second. And then we're going to have plus the first thing, which is just 3/4 times pi, times the derivative of the second. Our second we have right here is r cubed. Our second function is r to the 3rd power. So to take the derivative of this, we're going to have to just use our normal methods, but also apply the chain rule that we learned I think it was maybe 30 minutes ago when we introduced this. The fact that we have to use the chain rule in a problem like this one. So this is going to be 3r squared. And applying the chain rule means we get dr dt, derivative of the radius with respect to time. And then what are they asking us to find again? They want us to find how fast is the radius of the balloon increasing. So let's put into mathematical notation what that really means. How fast is the radius increasing with respect to time? So this would be dr dt. Makes it clear that they're asking us to find dr dt. So that is our goal here, dr dt. So just like with implicit differentiation we were doing before, we want to isolate dr dt. And I realize we're out of time, but let's just finish this real quick. I promise it won't take long. So this whole thing is 0. Then we have this right here. So this 3 can cancel with that 3. And then if we divide both sides by 4 pi r squared, we're going to get something like this. And then we want to divide, oh, I forgot, I already included r squared in that. We already divided by r squared. So now that we have this, they're asking about an instantaneous rate of change, meaning that we are plugging in a specific input value and seeing what the output value is, kind of like one of the problems you had on our recent quiz. So we're going to plug in 50 for our, well, actually, this is a bit misleading. We have a diameter. What we really want is a radius, because our differential equation we have right here is in terms of radius. So r would just be 25 centimeters. So this is going to be 1 over 4 pi times 625. 25 times 25 is 625. And then we also have dv dt, and they already tell us what that is. This right here, dv dt, derivative of volume with respect to time, is 100 centimeters cubed every second. Units aren't important right now. So we could simplify this. We could get 100 divided by 4 is 25, and then 25 over 625 is 1 over 25. So our final answer would be this. We would have derivative of the radius with respect to time would be 25 over pi. All right. Sorry we went over the time, a few minutes late, but I hope you guys found this useful. Like I said, we're going to be covering this more in depth on Sunday. All right, you guys are free to go. Enjoy the rest of your evening. I'll see you on Sunday.